Okay, in the previous session, we considered how to solve problems using the moment distribution method. And the problems we considered did not involve any so-called sway, okay, or settlements. So they were all problems where the kinematic indeterminacies were only rotations at joints. Okay. Now, when we consider problems with sways or settlements, uh, we will need additional equilibrium equations. So this we have already seen in the slope deflection method, right? So when there are sway problems, there is an added term to the moment balance. Okay, and there is an added equilibrium also which is needed, equilibrium equation, because the number of equations that we get is usually less. Okay, and whatever is the number of sway degrees of freedom, that is the additional number of equations that we require, even in slope deflection method. And that additional equation usually comes from the balance of the force which is in the direction of the sway. Okay, so if we are talking of swaying of a frame, we will in general write the horizontal force balance to get that additional equation. If we are talking about deflection of a beam in the sway direction, or deflection, then we will primarily be writing the vertical force balance in that case. Okay, so let us see how problems with sway can be considered through the moment distribution method. So the essence is the same, that whatever essence we used, or whatever method we use for slope deflection, same thing we will use for moment distribution, because moment distribution is nothing but another way of solving the slope deflection equations, right? So instead of solving the slope deflection equations directly, we solve them iteratively. That is the only thing that uh, additional thing that moment distribution as a philosophy brings. Okay, now let us say we have this kind of a frame where there is an off-center force applied at the beam of 32 kilonewtons, and let's say we have to find moments at all the joints. Okay, now once you have experienced solving many problems, okay, so once you have solved many problems and seen many problems, just by looking at this problem, you will know that this is going to sway to the right. Okay, that is to the side of the sea. Okay, but when we are starting to learn this method, in general, it is not possible to for us to visualize that whether it is a sway problem or not. Okay, so irrespective of in which direction it will sway is a different question altogether. But in the initial stages, we but sometimes don't even are able to tell whether it will sway or not. Okay, uh, so fortunately, moment distribution method offers actually a way to find that out as well. I mean, so does slope deflection, of course. Okay, so let's say that we don't know about sway at all. Okay, so even though if you have solved many problems, looking at this, you will know that this is a sway problem. Okay, but to start with, let us say we don't know about anything about sway. Let's say we don't think it will sway. Okay, so we consider it a normal problem, and we use the usual procedure for the analysis. Okay, now if we have to use the usual procedure, see in this case we have chosen both the lengths to be 5 meters, just for the sake of simplicity. So we know that all the distribution factors at each joint for all members will be 1, okay, except A and D, which will be 1. Okay, so for B and C, the distribution factors for BA, BC and for CB, CD, they will be both 0.5. Okay, and there will be fixed end moments only in the member BC, because AB and CD do not have any externally applied forces. So these fixed end moments we calculate. Okay, uh, so other fixed end moments are all 0, and the distribution factors are all 0.5 except A and D, where it is 1, which is a different obvious case. Okay, okay, so we are solving this problem now. So again, the first row is going to be label of the joints, then there is label of the members, then we have the distribution factors, right, and then we have the fixed end moments. Now, here we are just following the earlier process of balance and carryover, balance and carryover. Okay, so we will continue this balance and carryover process until we see that the imbalance of the moments is small enough with respect to the initial fixed end moments. Okay, so let's say we carry out all of this process and then we do the column sums as we had been doing, right? So then we get certain moments. Okay, so we have carried out the usual process. We have not worried about whether this frame will sway or not sway. Okay, so we have not worried about that at all. We have just assumed that we will, or in fact we have just adopted the usual method of solution, and we have eventually found out that there are some end moments which we have found out. Okay, now once we have found out these end moments, so after finding all of these end moments, assuming the problem to be a non-sway type or a regular type or the usual procedure, then we draw the free body diagrams of all the individual members. Okay, so we draw it for AB and we show the moments with their respective orientations. Okay, and from there we can calculate. See, for member AB there is a net clockwise rotation. Okay, so there is a net clockwise moment of 11.6 plus 5.8. Okay, to counter that, there has to be a counterclockwise couple which will be generated by the forces HA and HB, right? And HA and HB will be now same, equal, and that net counterclockwise couple will be this 11.6 plus 5.8 divided by L of that, which is 5. Okay, so this horizontal force in the member AB comes out to be 3.48 kilonewtons. Okay, similarly we will do force balance for the member BC. That will give us the vertical reactions. And again we can look at member CD. Now this member CD has a net counterclockwise moment of 5.46 plus 2.72. Okay, so the horizontal forces here, HC and HD, they need to produce a net clockwise moment or a clockwise couple, right? So that couple is given by when the forces, both of them are 1.64 kilonewtons. Okay, now we can combine all of that and we can draw the overall free body diagram. Okay, so we can draw the overall free body diagram of the system. Now in this what we see is that the vertical force balance is not a problem, that is satisfied. Okay, but if we do horizontal force balance, which is summation of Fx, right, that will be 3.48 minus 1.64. So there is a net horizontal force of 1.84 kilonewtons towards the right. Okay, so there is a net force on this frame. I mean, although we have solved it by equilibrating the joints through moment distribution, there is a net force which is acting, which means there is some problem. Okay, similarly if we take moment about point A, okay, that will be 5.8 minus 2.7 to plus 32 times 1, so that is the moment of the applied load, right, minus 5.17 times 5, that is from this vertical reaction. So we see that there is a net moment of 9.23 kilonewton in the clockwise direction. Okay, so basically the problem is that there is a net horizontal force and there is a net clockwise moment on the system after we have solved it through moment distribution method. Okay, now whenever this happens, this is an indicator that this is possibly a sway problem and we have not considered the sway. Okay, and this is how in moment distribution this information about sway or non-sway automatically comes out. Okay, so basically we have a system like this. Okay, so we have a system like this where there is a net clockwise moment of 9.23 kilonewton meter, and there is a horizontal force at the bottom which is unbalanced, which is 1.84. Okay, now the interesting thing to note is that if we do 9.23 divided by 5, which is the height, Okay, it comes out to 1.84. So what that is indicating is that this 1.84 is, uh, although it's a reaction force which is coming out, I mean, there should be another reaction force which we have not factored, or which we were not aware about, which is acting on top. Okay, and this top 1.84 and the bottom 1.84 is producing a counterclockwise couple of 1.84 times 5, okay, which comes out to 9.23, which is exactly the moment imbalance of the system. Okay, so what it means is we have actually solved a different problem. Okay, and the problem we have solved has a prop here, has a support there. Okay, and this top 1.84 which we were missing, that is actually a horizontal reaction uh, of that top support. Okay, so this top support, so we have actually solved a frame which has this support. Okay, and with this we have also found out that the reaction force of that support is 1.84. Okay, now we can use the same logic which we had been using for joints, right? We were freezing the joints, fixing the joints, and then allowing them to rotate, right? By applying the force which is by applying the moment which is required for equilibration. In this case, we see that there is a force which is preventing it from moving to the right. Okay, now we can balance it by applying an equal and opposite force to the right. Okay, so there is a reaction force acting to the left, which means if we apply an equal and opposite reaction force, or equal and opposite force at point C, thereby allowing that sway movement, okay, of the beam BC with respect to AD. Okay, so that is the additional thing which is now required. Okay, so uh, so we, for any problem, we follow the usual moment distribution method. Okay, if there is an unbalanced net force, that will indicate there is a sway. Okay, now uh, of course this amount of sway is also unknown. Okay, so but if we see that there is a net unknown, net imbalanced force, then we now have to account for this. Okay, so basically what it means is that we apply a force of 1.84 kilonewton, okay, to balance that reaction force that is there, and in doing so we induce a sway, right? This is just like inducing a rotation by applying a moment. So we apply a force to apply a displacement. Okay, so we apply a 1.484 kilonewton force at the beam level BC, right? And that will induce this delta. Okay, so this delta is the horizontal deflection of the top of both the columns. Okay, and since these are connected to the same beam, and beams we have assumed as of now, let's say, actually rigid, which means they can actually elongate or shorten, right? So the both these deltas can be assumed to be same. Okay, so now basically we need to do something about this delta, which is the additional information. Okay, and before we go further, you may recall that the fixed end moments due to support settlement for a beam, right? So if a support A and B were there, and B support uh, you know went down in a clockwise direction. So if this phi was, if you recall, delta by L, right? So if the net chord rotation due to the support settlement was in the clockwise direction, the moments induced due to this, the fixed end moments induced due to this delta settlement, that are in the opposite direction, or they are with the minus sign, and they are 6 ei by L squared times delta. Okay, and now we have a system where the columns AB and BC are going clockwise with, due to this delta. Okay, so delta is to the right, and hence AB and CD have a clockwise rotation sense, right? And in this case, these rotation magnitudes are also equal because deltas are same and the lengths L are same. Okay, so what it means is that now in to balance that unbalanced force of 1.84, now we have to induce this delta, unknown delta. Okay, And to consider the effect of this induced unknown delta, we can consider the friction moments which are generated due to support settlement or due to sway. Okay, so what it means is MFAB, BA, CD, and DC, all of them are 6 EI by L squared delta, and because delta is unknown, let's call this moment as M bar. This M bar is also unknown. Okay, so delta is unknown, M bar is also unknown, and because there is no relative settlement of B and C vertically, the friction moments for the beam BC will be both zero. Okay. Okay, so now in order to proceed, we know that we cannot deal with unknowns in the moment distribution table. Okay, so what we do is, and this is very interesting, we assume m bar to be, let's say, minus 100 kilonewton meters, right? Now, this is an arbitrary choice. Any convenient number can be chosen here. Okay, and the consequences of choosing this number will become clear later, and we will see how this can be leveraged. Okay, so we choose any convenient value for this m bar, which is the friction moment due to sway. Okay, it is actually unknown, but we have assumed some number. Okay, now if we start with these set of friction moments m bar, which we have assumed to be minus 100, we can again carry out the moment distribution table, right? And once we do that, we will again get some MAB, MBA. We will get all the end moments, right? So the procedure would not differentiate between whether it is an assumed value or whether it is an actual value. Okay, but once we get all of those values, we will see that the actual m bar, right, which was 6 ei by L squared times delta. So this 25 is nothing but 5 squared, which is equal to L squared for the current problem. Okay, so what we see is that see, if m bar gives a certain moment MBA, right, whereas it should have been 6 ei by L squared times delta, what it means is that all the moments which we actually find out using this minus 100, they have to be scaled by this amount. Okay, so this is very simple unitary method. So basically we assumed minus 100, we received some, let's say, MAB or MBA, right? But if this was 6 EI by L squared, 6 EI delta by L squared, then this would be MAB divided by minus 100 times this 6 EI by L squared times delta. Okay, so this is the very simple logic. So what it means is that once we calculate MAB, MBA, etc., everything has to be scaled by this amount for us to be able to get actually, if 1.84 was applied, then what would happen, right? And to calculate EI delta, we can use the overall force balance. Okay, now let us see how it works. So now everything is the same here, except that now in the fixed end moment, we have used the assumed uh, minus 100 values. Okay, so in the fixed end moments, we have used the assumed values. Then we carry out the moment distribution procedure as it is. Okay, and eventually we get here where the balancing moments are small, and so we sum them up. Okay, and we assume that we are making some small approximations. So instead of minus 80.08, we are writing minus 80 and so on. Okay, so these are the additional moments which will come due to sway. Okay, so the first set of moments were without sway. These are the additional moments which will come due to the sway, and we know that all of these moments have to be scaled by 2.4 times 10 to the minus 3 EI delta. Okay, and this delta is not known yet. Okay, okay, so now again we consider horizontal force balance. Okay, so for each member we calculate the horizontal forces. Okay, we see that now these horizontal forces are you know again imbalanced, but in the same direction, let's say. So the horizontal reactions are 28 and 28. So what it means is that by assuming minus 100 as the moment, okay, what is the force that we have solved for? Okay, so we wanted to solve for a case where the net applied p is 1.84 kilonewtons. Okay, but we actually solved for the case where p is equal to 56, right? So this net reaction to the left and the applied force to the right, they have to balance out. Okay, so instead of solving it for p equal to 1.84 kilonewtons, we have actually solved it for p is equal to 56 kilonewtons. Okay, and this is obviously because of the arbitrary choice of m bar. Okay, because we did not know what will be the m bar for p is equal to 1.84. I mean, we had no way of finding that earlier. We chose a certain value, we solved for it, and by back calculation, we are now able to see that the force that we actually solved for is 56 instead of 1.84. Okay, and this is again coming from simple force balance. Okay, so what we know now, that any quantity that was calculated using that assumed minus 100, that has to be scaled by 2.4 times 10 to the minus 3 EI delta. Okay, which means that this force that we have solved for, P is equal to 56 kilonewtons, that also has to be scaled by the same amount. Okay, but the beauty is that when we scale it by the same amount, we should be getting the actual EI delta for which which is the unknown sway. I mean, the unknown sway earlier can now be calculated, right? So 56 times this factor equals to the force that we wanted to solve for, right? That gives EI delta. Okay, and once we get EI delta, we can calculate this multiplication factor, and then we can calculate the actual moments due to the sway, right? And for simplicity, we can calculate the numerical value of the scaling factor. So that is 2.84 times 10 to the minus 3 EI delta. Okay, and if you really see from this equation, so this 2.4 times 10 to the minus 3 EI delta, that comes out to the desired force for which we wanted to solve divided by the actual force for which we analyzed, right? So this is 1.84 divided by 56. Okay, so again, when we are using this method in practice, we need not actually calculate EI delta. We can simply calculate what was the force that we wanted to solve for, that was P desired, and what was the force that we actually ended up solving because of the arbitrary choice of m bar, right? This arbitrary choice, and we can simply divide them, and that will be the multiplication factor for all the moments that we calculate. Okay, and now we have two cases. One where we did not pay attention to sway or non-sway, we just solved the problem, and that ended up giving a problem, giving a system which was imbalanced in terms of force and moment, right? So we applied a balancing force which also balanced the moment, or which also should have balanced the moments, right? So we applied that. So now these two different problems can be added, because we are in the linear elastic solution schemes or systems, right, where displacements and forces can be added, right? So the overall end moment MAB can be calculated like that. So we write the first one, which is the no sway version of the frame, right? So that is plus 5.80 times the moment which comes from the sway only version, which is when we apply the horizontal force, right, times the multiplication factor which we just calculated. Okay, so that gives the overall moment MAB. Okay, and like this we can calculate all the other moments by combining the non-sway and the sway versions, right, with appropriate scaling factor. And once we calculate all of these moments, we can again draw the free body diagrams, as you can see here. And once everything has been factored in, the overall structure will be balanced in vertical forces, horizontal forces, as well as moments. And that is something you can check here, that the horizontal forces are balanced now. They are equal but in the opposite direction. Okay, so there is no net force and there is no net moment acting on the frame, right? And only when the overall free body looks like this, it is fully equilibrated. Only then we can stop, right? So in the earlier case, when we considered uh, that no sway was happening, uh, you know this free body diagram was not actually in equilibrium. Okay, so that prompted us that there is something more to it, and that is where we undertook the sway procedures. Okay, so we considered the only sway part, and we applied a force which was the imbalance. Okay, then we found out what was the actual force we ended up solving for due to the um, assumed moment m bar. Okay, and then we found out what was the um, scaling factor, and eventually we are combining both of them, we are able to solve for that. Okay, so this is how moment distribution procedure can be used for sway problems.